Hey, this is Z Hao, and this is my Lab 1 report for Physics 2211 on constant velocity motion. This slide outlines the four main parts of my presentation. First, the overview will explain the purpose of this lab. Then I will cover the key physics concepts, mainly Newton's law. After that, I will explain the procedures, both experimental and computational. And finally, I will compare the result in data analysis and conclusion. The goal of this lab is to compare a real motion to a physics-based computational model. I observe the motion of a masking tape roll moving at a constant velocity and analyze it using tracker. Then, I simulate the same motion using closed grip. This lab demonstrated Newton's first and second laws, especially the case when the net force equal to zero. Newton's first law states that an object will stay in motion at constant velocity unless acted on by an external force, and that's why the tape keeps rolling smoothly. Newton's second law shows that if the net force is zero, the acceleration will be zero, which explains the constant velocity. And these two equations come from Newton's second law and describes the motion update over time. First, the velocity update equation. This tells us that if there's any net force, it changes the object velocity, but in this case, since the net force is zero, velocity stays constant. Then, the position update equation. This shows us how the object's position changes each frame. It moves forward by velocity times time. I use this to update the tape's position in my simulation. In this lab, the system is the masking tape roll. The surrounding includes the floor, air, and any force acting on it, like friction or gravity. Experimental setup. I record a video of a roll of masking tape moving across my living room floor, then import the footage into Tracker. I calibrated the video using the tape's known denominator of 0.114 meters, set the axes, and track the tape's motion frame by frame to get the position time data. For computational model, I used the article in closed grip to simulate motion. I enter the initial velocity based on the tracker's data and set the time step to match the frame rate. I assume zero net force, so the code used at a constant velocity update to predict the position over time. Here's a quick video that I took of the roll of the masking tape going at a constant velocity in my living room. And all these red dots that you see are the center of the mass at each time frame. And you can see the graph of position versus time on the right appears linear, and I'm going to run a computational analysis to see whether this is true or not. Here is a snapshot of the data from the tracker for the first two frames. You can see the change in time, initial position, and the final position. I used the equation V equals to change in position over change in time. I was able to calculate the initial velocity to be approximately 1.927 meters per second. And this value was then used in the simulation. PostScript, I set the initial position and velocity using tracker's data, which is on the top right column. Then, I used the update velocity formula to find the final velocity, which is the initial velocity plus net force over mass times change in time. But since the net force is zero, velocity stays constant. And then the update position equation is final position equals the initial position plus average velocity times change in time. But since velocity is constant, the average velocity is just initial or final velocity. And this loop runs until the simulation matches with the video duration. I also plot the position and velocity to compare the experimental result on the next slide. This graph shows the experimental data and computational prediction. Both curves are linear and almost identical, which confirms that the model accurately represents the tape's motion. Minor differences happen towards the end of the change in time range because the speed of the observed roll decreases relatively to predicted, suggests that there are some net force acting on the tape is against the tape's motion, which is the friction of the carpet. There could be some experimental errors like calibration inaccuracy, clicking errors in the tracker, or slightly changes in direction. And in this model, I assume there's no frictions or resistance and perfectly smooth motion, which is not true in real life. And this simplification may explain why the experimental velocity slightly decreases over time. Together, these factors could cause a small mismatches in velocity between the experimental and the computational model. If I flip the axis in tracker from positive to negative, the velocity will become negative. but the magnitude and behavior will remain constants. For the second question, although we observe zero net force, we cannot say how many specific push or pull are causing that balance. The friction, normal force, gravity, and air drag all interact, but we observe only the net effect, which is constant velocity. Lab showed me how experimental tools and simulation tools can work together to demonstrate the core physics principle. I hope you can learn a thing or two from this lab. Thank you.